Okay, so picture this. A world where your coffee maker already knows you're waking up, or an industrial sensor can literally predict its own failure before it happens. I mean, it's an amazing vision, right? A world full of truly smart objects. But there's a huge, kind of hidden problem standing in the way of making that a reality. Let's break it down.
So here's the core of the problem, the big conflict. On one hand, you've got these massive AI brains, these deep neural networks. They're incredibly powerful for sure, but they are absolutely starving for energy and computing resources. And on the other hand, we have these tiny Internet of Things devices that we want to make smart. You know, things that are meant to run on little batteries and have just a tiny bit of processing power.
So that really brings us to this central challenge, the impossible equation. How in the world do you squeeze that giant, power-hungry AI brain into a tiny little device that's designed to just sip power? Honestly, it's one of the biggest puzzles in tech today.
So, how do we start to solve this? Well, the first and, the most obvious idea is pretty simple. If the AI brain is just too big for the device, why not just split it in two? Let's see what that looks like. This idea has a name. It's called split computing. The strategy is, instead of trying to do all the heavy lifting on the small device, you do a little bit of the thinking locally, right there on the object, and then you send that partially processed info up to a big, powerful cloud server to finish the job. It's kind of like a team effort between the little device and the big cloud. When you look at it this way, we've really got three options. Option 1, try to run the whole AI on the device. We already know that's pretty much a non-starter. Option 2, send all the raw data to the cloud and let it do all the work. But that's slow, and it totally drains the battery. So that makes this third option, the split approach, seem, well, perfect. It looks like the ideal middle ground.
But, as it turns out, this really elegant-looking solution has a very counterintuitive flaw that's hiding just under the surface.
Right? I mean, it seems so logical. Do a little bit of work, send a smaller file, and save energy. What could possibly go wrong with that?
And this is where things get really interesting. You've got this huge disconnect between the theory and the reality. The graph on the left shows what we expect to happen. The more processing you do on the device, the less data you should have to send. Makes sense. But the graph on the right, which comes from actual research, shows what really happens. The first few layers of a neural network, they don't shrink the data. They actually make it explode, creating this massive data bottleneck that makes sending it halfway through the process just incredibly inefficient.
So, if the AI's brain is bloating the data like this, researchers had to figure out a way to put it on a diet. And that led to a really clever software solution. The solution they came up with is this cool three-step strategy. First is something they call waist tightening, which is all about aggressively compressing that bloated data. Second is pruning, where they intelligently snip away unnecessary parts of the AI model on the device itself. And finally, they optimize both of those steps so they work together perfectly, maximizing every little bit of efficiency.
The secret sauce here, the key to that waist tightening, is a technique called one-bit quantization. Now, think of it like this. It's like taking a beautiful, high-definition color photo and reducing it down to a super simple black and white sketch. The data becomes unbelievably small and so easy to send. But as you can probably guess, you lose a ton of detail and accuracy along the way.
So how do you fix that massive accuracy problem? Well, that's the final, brilliant piece of the software puzzle. On the server, they built a second AI. It's called a quantization compensator network, or QCNet. And its only job is to take that super compressed sketch that the device sends it and expertly reconstruct the original high-quality information. It uses the server's massive power to basically fill in all the gaps. Okay, so the algorithm is solved. In theory, we have a way to make this work. But when you try to actually deploy thousands or even millions of these devices out in the real world, a completely different and much more practical problem pops up. This quote from the innovators at a company called AI-Chip, it just gets right to the heart of the matter. It doesn't matter one bit how clever your algorithm is if the device itself isn't reliable. And for all of these devices, the single biggest point of failure is power. Yeah, when you go from the lab to the real world, you run into a whole new set of headaches. You've got unpredictable costs, network failures, and you're often using chips that are way too powerful and expensive for the simple job they need to do. Out in the field, uptime and reliability are everything. A brilliant AI that's turned off is, well, it's just a useless piece of plastic. And this is where AI-Chip's solution comes in. They didn't build another AI processor. Instead, they developed a specialized chip called an AI Power Management Controller. Now, this chip's job isn't to run the fancy vision AI or whatever. No, its job is to be the governor of the device's most critical resource, its power. It's all about making sure the device is stable, efficient, and, most importantly, always on.
So what we're seeing here is a really crucial shift in mindset. The goal is no longer just about hitting the highest possible AI performance score. The goal is to make a system that is deployable, something that's affordable, reliable, and that just plain works, day in and day out, at a massive scale.
And this brings us to the final synthesis, where these two very different approaches, one from academic research and one from industry, actually come together in a really beautiful way.
This table lays it out perfectly. You can see how the two solutions just fit together. The academic software solution, it tackles the problems of energy use and that massive data volume. The industry hardware solution from AI chip, it tackles reliability and cost. See, they aren't competing with each other at all. They're solving different parts of the very same equation.
And that really brings us to the ultimate takeaway here. You need both. The incredibly clever algorithm is what makes this kind of AI possible in the first place by solving that data bottleneck. But it's the smart, focused hardware that makes it all practical, reliable and affordable enough to actually put out in the real world. It's the perfect handshake between software and hardware.
So, this leaves us with a final thought to chew on. Maybe the future of all this isn't about trying to build one single perfect, all-powerful brain to cram into every device. Maybe, just maybe, it's about building a distributed, resilient nervous system where every single part plays its own unique role perfectly, from the clever algorithms to the simple, reliable hardware, all working together in harmony.